All right, let's talk about the heart. Okay. Up here, I'm going to draw a heart. That's not amazing, but gets the job done. So up here we got our atria. And down here we got our ventricles. We got our left ventricle and a right ventricle. Now somewhere around here we have a V node. This AV node regulates basically how fast our heart beats. There's receptors on it, and within the AV node there's pacemaker cells. Now the cells of the heart are all connected, the contractile cells with pacemaker cells, via gap junctions, which allows for ion flow. So it allows for smooth, rhythmic contraction that we need with the heart. So, as such, there's going to be some interesting action potentials related with both contractile cardiac cells and pacemaker cells. And in this video, I seek to address those two. First off, we're going to talk about contractile cells. All right, let's talk about contractile cells first. So I'm going to draw this graph here. Should look something similar like we're used to. I'll make that a little straighter here. Okay, down here we have time. Okay. Here, our bottom will be negative 100 millivolts. Negative 80 right there. Negative 60 right there. Well, we should scale it a little bit differently here. Put negative 80 right there. Negative 60. Negative 40. Negative 20. 0. 20. 40. And yada, 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 so on. Okay. So, we've learned that the resting membrane potential of most neurons is negative 70 millivolts. The resting membrane potential of pacemaker cells is almost negative 90 millivolts. What does that tell us? Well, that tells us how pacemaker cells are polarized. They are almost entirely polarized by IK1 potassium channels. So, the threshold is around here. Okay. They keep the cell at around almost negative 90. And this is called phase 4 of that cycle. And here we have IK1. Okay. Now, upon reaching an action potential, it spikes up really fast because immediately what opens are these sodium channels. And since contractile cells use sodium channels, we get a really aggressive spike in potential, not that high, somewhere around there. And then as soon as we reach a certain, like around negative 20 or a positive 20 millivolts, what will open are these transient outward channels. So we have ITO1, and then we have ITO2. So ITO1 is a potassium efflux channel. and ITO2 equals calcium activated phase 4. This is phase 0 right here, and this little dip right here, this is phase 1. Oops. Now, why did we open up these ones? Why do we jump right up and then we go right back down? So what happens is as the membrane potential goes up, we open up these voltage gated channels. A potassium efflux channel, the ITO1 transient hour channel, and the calcium activated chloride channel. And this will hyperpolarize the membrane a little bit to prepare for phase 2. And here's phase 2. And in phase 2, we have 4 channels that decide to open. 4. With L-type calcium, IKUR, IKR, and IKS. Not that long, but you get what I mean. So, this is called the plateau phase. This is probably the most important phase of heart contraction, as it's how we avoid tetany, prolonged contraction of the heart. We don't want the heart to behave like skeletal muscle, where we flex it and then we can relax it based on our own control. We want the heart to contract and relax rhythmically as the pacemaker cells are controlled, so that we get a smooth pumping action, so that the heart contracts as soon, because you got your heart over here. Here are the atria. So as soon as blood goes from the atria to the ventricles, we want the ventricles to contract, and so they will. And we want the atria to contract at the same time, when there's actually blood to push. We don't want it to contract before and build up pressure, as that blood can't even get into the ventricula. And so that is why this plateau phase is important. So what happens is, here's our cell. So when the L-type calcium channels open, calcium will rush in. And this will usually cause a depolarization of the membrane. However, we have these potassium channels that are open. And so as calcium is running in, potassium is coming out, which keeps the membrane potential relatively consistent during the plateau phase. Now, this calcium, cardiac muscle behaves a lot like skeletal muscle. The calcium will go in, open up ryanodine receptors in the sarcoplasmic reticulum. Calcium will spill out in the cytosol, activate myosin motorheads, and then boom, boom, we get contraction. So that's why this phase is important. This phase can be modified and can be manipulated in order to basically modify heart rate. So that phase is important. And here we have phase 3. Repolarization of the membrane. And the channels that are mostly responsible for this are these ones as well. A little bit of IKUR, but mostly IKR and IKS. These are 3 types of potassium channels that open depending on the time frame. This one will open first, the potassium ultra rapid, then the rapid ones and the slow ones. And then IK1 will open and then establish our resting membrane potential close to negative 90. I'll make that a little deeper. So yeah, that is how action potentials work in pacemaker cells. So just to go over, we have potassium channels maintaining our negative 90, close to the equilibrium for potassium maintaining are negative 90 millivolts. Sodium channels will open up, allowing sodium to rush in, depolarize the membrane. These transient outward channels will then hyperpolarize it, because you have chloride channels, and then you have potassium channels, it's an efflux channel. And then during the plateau phase, we maintain this sort of plateau in order to prevent tetany, so that the muscle can contract at the right time. And then during phase 3, potassium channels, these will stay open, hyperpolarize the membrane even more. IK1 takes over, and then we're ready for another cycle. So that is more or less how action potentials work for contractile cells. Okay, talked about contractile cells, now we're going to talk about pacemaker cells. Alright, I'll show you the cycle real quick for a pacemaker cell. Alright, here we go. And get a little graph going. Draw a straighter line. Get a little graph going here. Times on the bottom. Like negative 60 millivolts this time. We'll do 20 up here. Threshold will be around negative 40. 0 right there. Okay. Awesome. All right. Okay, so my drawings aren't perfect, but you notice here that our pacemaker cells don't exactly have a resting membrane potential. That's because they're constantly, always, either being hyperpolarized or depolarizing. And today we're going to talk about a lot of interesting channels that make that possible. So starting with phase 0 here. I guess I should go right here too. Talk about HCN. Okay, so the most interesting thing about pacemaker cells is that there is a voltage gated channel that opens upon hyperpolarization. And they're called funny channels. Now, funny channels are also activated by cyclic nucleotides, so like CAMP, and we'll talk about that in a second. Yeah, we'll talk about that in a second. Okay, so what these do is they activate sodium channels, very tiny sodium channels, to allow a trickle of sodium and its slight depolarization like this in the cycle. So as the cell is depolarizing here, T-type calcium channels, means transient, quick, will open and calcium will rush into the cell, thus getting it to cross threshold. And then as soon as we cross threshold, we activate L-type calcium channels. Now what will happen is that calcium will rush into the cell. Here's my cell. Calcium will rush in, depolarizing it. And upon depolarization, we'll have potassium channels open. And this will start to repolarize the membrane once again. And, well, then upon reaching threshold, these funny channels will open again. They open upon hyperpolarization. Sodium will start to come in, trickle in, and it will begin the cycle again, depolarizing. T-type opens, L-type opens, depolarization, potassium opens, boom. And that's how this sort of cycle goes. Depolarization, hyperpolarization, depolarization, hyperpolarization. Now, one thing I talked about was how these cells are sort of the, they regulate how fast the cardiac contractile cells, basically how fast they cycle. And so if we increase the amount of action potentials we get out of the pacemaker cells, we actually increase heart rate. Now, how do we increase heart rate? Well, what we remember is epinephrine. So epinephrine will bind to G proteins on these cells, GPCR, G protein coupled receptor, and then that will dissociate. Alpha subunit will then bind to adenylyl cyclase, causing an increase in cyclic AMP. Now, funny channels are actually activated by CAMP. So when we have an increase in cyclic AMP, we have an increase in activity of funny channels. So heart rate will go up as the cycle will cycle more, causing potentials to propagate, more potentials to propagate across the heart in their cycles, increasing heart rate. Now, interestingly enough, there's another type of there's parasympathetic as well. There's parasympathetic activation of, or parasympathetic inhibition of these channels as well, or these cells as well. So what will happen is that there's also here acetylcholine potassium activated channels. So acetylcholine will activate potassium channels in the membrane of pacemaker cells, causing hyperpolarization and causing a decrease in heart rate. And so that's how the parasympathetic nervous system can regulate as well, these pacemaker cells, to decrease heart rate, and the sympathetic can cause an increase in heart rate. Okay, I don't know what happened, but I guess I forgot to record, but here's what happens. Talking about EKGs here. So these raises are caused by vectors. As you have negative charges and positive separated from positive charges here, or as the cell depolarizes, right? That will cause a rise, and as more get depolarized, it'll rise, but it won't rise as far, but it still continues in time. So I sort of drew all this out. I'm too lazy to really erase it, and I just recorded. I just forgot to. Okay, so basically, this is what a normal EKG looks like. So you have a P wave come through, and the P wave is the depolarization of the atria. So, right, normally we'll have positive charges outside the cell membrane. These negative charges represent depolarization. So, atria are not very large compared to the ventricula, and so that's why the P wave is a sort of just a raised bump like that. And then this weird part of the heart is it'll actually depolarize from the positive to the negative. And as it depolarizes from positive to negative, it'll make this little dip right there. R wave is the largest one, of course, and it's when we get depolarization of the bundle of His through here throughout. So here we go. So this is the R wave coming through and depolarizing all the bundle of His and all that. And that's why it's so large. And then we have another inverse wave as the S waves depolarize up here, causing another little dip. And then coming back. And then the T wave equals hyperpolarization of the membrane. It's just this is the T wave coming back. It's a positive vector going to negative. That's why we get another little rise. So yeah. That is EKG in like 2 minutes. All right, let me erase this. Let's talk about STEMIs. STEMI stands for ST elevation myocardial infarction. And it happens due to current of injury. Now we'll explain that, but first we got to know about hypoxia. So I'm going to draw our heart. Here's our heart. That's not very good heart. Focus. Okay. Okay. Atria, ventricle. Okay. Right ventricle, left ventricle. Okay. Now supplying blood to the heart. This is a large coronal artery, and it kind of branches out like that. Now this part of the heart is super thick, and so say that there's a blockage up here, atherosclerosis or whatever, plaque, it can cause O2 to get stuck. So that means this part of the heart might be receiving less oxygen. Now, if you've ever taken Bio 180 or just breathed, you know, oxygen, you need it to live. So, what happens when we have a decrease in oxygen? Well, we know that equals a decrease in adenosine triphosphate. And what does a decrease in ATP mean? Well, that means we can't power, no power for the sodium potassium pump. And what happens when we can't pump sodium out of these cells? Well, that means our potassium channels aren't very effective because there's no reason to leave the cell. And so that means our threshold increases or decreases. Well, our rest RMP will then increase. So in order to counteract that, evolutionarily, we've evolved something called, in our contractile cells, called an IK-ATP. Now this is a potassium channel that's inhibited, IK-ATP I think, inhibited by ATP. So when ATP is low, this potassium channel will open and we get more or hyperpolarization. This hyperpolarization will cause, this hypoxia will cause certain positive charges to build up on the outside because we have hyperpolarization of the membrane of these hypoxic contractile cells. Now, what does that mean for our EKG? Let's see. It means this. You see that? All right. Oops. See that? Our T wave got inverted. Why? Now, these cells, they still depolarize, they still go through the cardiac cycle, but they're upside down. No, they're not upside down, sorry. They just repolarize, they hyperpolarize a lot quicker than the other surrounding cells, causing an inverted T wave. As now, so we have our positive and our negative lead right here, hyperpolarization will happen here first rather than in the epicardia first, and that will cause inverted T wave because positive is going to positive, causing an invert. So that is slight hypoxia. Slight hypoxia. Okay. Now we're going to talk about end STEMIs and STEMIs. First, we're going to talk about an end STEMI. End STEMI. And this will happen under severe or moderate hypoxia. Moderate / severe hypoxia. Okay. Draw the heart here. Okay, I almost been hard at that time. Okay. So we have our arteries over here, right? They're feeding our heart. We have our blockage right here, and it's a little bit more severe, causing even less oxygen to go to the heart. Now, even more cells will stay depolarized. This is bad. Not so bad that it's bad, though. It's bad. Now, how does this affect our EKG? Well, here. So Here's, say, our normal isoelectric point when there's no charges separated. And here's where our EKG would be. It would actually be above this. Everything will look normal, except this. That's ST depression. You can see that as our S wave tries to depolarize here, these cells won't depolarize, and so it won't go as low. It'll go a little wider. And as the cell tries to repolarize, we get our repolarization vector. It won't be as high, right? It'll be a little bit lower like that. As these cells stay depolarized constantly. That's called an NSTEMI for non-ST elevated myocardial infarction. Now, what does a STEMI look like? STEMI occurs when we have here's our right atrium. We have something that's called a transmural infarction. Where all these cells right here are hypoxic and they stay depolarized. Current of injury. Our EKG will look relatively normal until we get to ST elevation. Our normal isoelectric point will actually be higher than where our EKG is. This will cause elevation. ST elevation. Because as the S wave comes, R wave happens, but then the S wave comes, what will happen is it'll be higher along with the T wave. As it repolarizes, it'll be higher. Yeah, that's how STEMIs work. Oh wait, whoops. That's a STEMI. STEMI. Okay, now we're going to talk about lusitropy and ionotropy in a cardiomyocyte.
This can't be a thing that's in your
Lusitropy
No.
equals speed or just
It's
equals relaxation rate of a muscle cell.
Turning into a transfiguration.
And then ionotropy
Oh my gosh.
equals contraction strength.
Physiology, that's so silly. But we didn't see this. No, we just know it's
Similar
there.
structure. but
So,
close enough.
Ugh.
how does this happen? Well, cardiomyocytes luckily only have sympathetic receptors.
Yay.
So epinephrine will come in, bind to this decoupled protein receptor,
Okay, major
and then this alpha subunit right here
Let's see. This, how do we do this?
will dissociate.
This one, we pull alpha.
And upon dissociation,
They're both
They're both
equally.
alpha subunit
Yeah, they're both
will
equally.
go and activate adenylyl
But
cyclase.
it's kind
And now
of
adenylyl cyclase
Yes.
will cause an increase
Trans is more stable.
in cyclic
Uh-huh.
more
AMP.
often than not.
Now, how does this affect our lusitropy and ionotropy?
Yeah, I forgot
Well,
what it was. E is
cyclic AMP will go
cis.
No.
and will bind
Same side.
to L-type calcium channels, making them more readily, easier to open, allowing calcium to flood in.
I just feel like it should be the opposite. I just
And
feel
now
like
this,
it should be
if we know how
an
cardiomyocytes
trans, 'cause it
need
just-
calcium to contract,
it
this will
looks like
increase.
trans.
That does make more
Ionotropy.
sense, but it's based off of like some.
CAMP will
We
also
need to stop
go and it will
making up things
activate
that aren't
protein
different.
kinase A. Protein kinase A will then inactivate calcitamin, preventing it from inhibiting this RYR channel, allowing calcium
Good heavens.
to slip in right there,
Worked our way down.
or to open it up,
I got scared.
and then calcium will activate it, and then you get calcium slipping out, causing an increase in ionotropy. PKA will also go and it will phosphorylate phospholamban,
Okay.
causing it to dissociate from a Circa pump, thus activating it. And now Circa
Phenyl group.
Okay, that's
can more
okay.
effectively pump
Right, so that's
calcium
gonna wanna go
back
back to
into the sarcoplasmic reticulum, thus increasing lusitropy.
This is a phenyl group.
Effectively, this correlates with an increase in heart rate, where we need
Yes, so it is shock.
a greater contractile
So
strength
that is gonna work.
and a faster relaxation rate to get a faster heartbeat rate.
See, you want to see.
So that is how
And
epinephrine causes increased lusitropy and ionotropy in a cardiomyocyte. Okay, now we're going to talk about how cardiac muscle contracts and how calcium activates it. It's exactly the same as skeletal muscle. So you got your T tubule here.
That is a big
Yeah,
golden
you're-
face.
Yeah, you're welcome.
The red
T
goes
tubule
up
right
and
here.
over.
Just move it to a secondary position.
Now,
It's gonna be slower.
here's your like L-type calcium channel
Actually, no, I don't think
connected
there's a
to the
difference
RYR,
Because if anything,
Because it would just pull from the Hoffman,
right?
right?
So here's your sarcoplasmic reticulum.
I actually
And
don't
on the
think-
secondary
So-
position?
yeah.
Action potential happens,
Actually, yeah, it
calcium
wouldn't change. I was thinking.
enters, this flips open, and calcium
Concentration of that is increased rate will increase.
spills into the cytosol.
Just because
Then here's our
more and
contractile unit,
faster, because they're not as spread
actin long
out.
filament, short
Yeah,
filaments.
exactly.
Yeah,
Here's
yeah, be right.
actin up here,
No! Instead of
tropomyosin, keeping it on there. Here's
This one?
troponin.
No.
This one.
Calcium, right, binds to troponin, causes it to release, allows myosin, there's actin filaments, allows myosin to come
What does it
in.
say?
You got your
Increase and
ATP,
increase.
phosphorylates,
It will go faster.
and then you have it in its cocked position
Secondary
with
position.
the inorganic phosphate, ADP, power stroke,
Because it favors E2 more than S.
that comes off, and now ATP comes on, binds, phosphorylates again, and then you get your
Yes.
cocked position.
That's okay, that's okay, this one's only 2 parts and it's good.
Sure.
It's good.
And that cycles, right? And then you have like 3 of them. There's another actin, right, in the single contractile sarcomere.
No, I don't know.
And that's how cardiac muscle works. It's exactly like skeletal muscle.
No,
And then calcium
Steel, this one's
will get fed back into the sarcoplasmic reticulum
still E2.
via Circa pumps
It's going to pull
It's
from
gonna do the
the
Hoffman.
to stop contraction. Calcium
Look at our
back
base.
in via Circa pumps.
Oh,
So that's basically how it works. Okay. All right. Today we're going to talk about this graph here. This represents cardiac cycle. So, right, you have your heart here. I'm going to draw a little anatomy picture just so that we can understand what's going on here. So you got your heart here. Then you got your aorta going out to systemic circulation in your pulmonary vein. You got the atria, and then you got your ventricles here. So, this is pressure in milliliters of mercury. Here's diastole right here. Whoops, need a better marker. Diastole represents right here. And then systole represents the contraction. Okay, let me explain this. So, first we're going to talk about aortic pressure here. So whenever we have these pressure changes, basically blood will move from high pressure to low pressure. It's simple. You squeeze a tube of toothpaste, you increase the pressure on the end of the tube, and it squeezes out the toothpaste, right? So the atria here have a higher pressure than the ventricula. So what will happen is here, atria will pump in to the ventricula at the same time. Atria then goes to the ventricula. And as they pump in, mitral valves, the AV valves, close. Once blood is in the ventricula, it will contract, and you'll get this isovolumic contraction right here. Volume doesn't change, pressure does. And so this will squeeze, we're going to talk about the left ventricle here, squeeze blood into the aorta. This pressure basically causes the aortic valve to open. And you notice for a second here or so, the pressure in the aorta is actually higher than the pressure in the ventricula, yet blood is still flowing out because the aortic valve hasn't closed. Now, why this happens and why the blood doesn't flow back into the heart is because basically the blood was pushed out with such force and has momentum that it just leaves and gets into the aorta. And right here, the aortic valve closes. Then we get another spike in pressure in the aorta. And this is because as the aorta expands, it's a stiff sort of wall of flesh. It will contract back together, and that will increase pressure momentarily. And then it will drop, ready for another contraction. The ventricula will contract, mitral valve opens, allowing blood to come into the ventricula, and then we get another cycle. After diastole, we get another cycle of systole. So, yeah. So the sounds we get when the aortic valve opens, we get a lub sound. And when it closes, we get a dub sound. Boom, 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 boom. And based on how we can hear these different sounds in the cardiac cycle, we can figure out if something is wrong with the heart.